Please welcome Denise Fitzgerald and Tim Keir.
Hi, everyone. I'm Denise. I'm a group leader of mechanical engineering in MIT Lincoln Laboratory, and I'm also responsible for the digital engineering transformation at Lincoln. And today I'm going to talk a bit about evolution, transformation, and extending the digital thread into the area of system development. And I'm joined here today by Tim Keir from ARIS. I said to Tim a little while ago, I remember ARIS and ACE in the olden days where a lot of folks at ARIS would get up and do live demos. And so he volunteered to do a live demo for us to illustrate a lot of the points that I'm going to be talking about. So thank you, Tim, for volunteering to do that. So let me tell you just a little bit about Lincoln Laboratory. We are part of MIT, although we're not part of the campus. So we're not an educational organization. We do applied research for the U.S. government, primarily the Department of Defense. And we're a special kind of organization called a federally funded research and development center. So which means we advise the government, we look for cracks in national security, and we suggest technology solutions, and the government funds us to demonstrate those solutions. So on the left, you can see some of the areas that we develop technology in. I work in the engineering division, and we do end-to-end development of hardware. So anything from systems analysis, early concept development, all the way through to prototype demonstration, deployment, and technology transfer back to the government or industry. So just as an example, on the left, here's some of the technology that the lab develops, and that could be anything from algorithms to advanced wafers and imaging circuits, things like that. On the right are examples of some of the hardware that we've developed, and hardware could be anything from something that sits on top of a bench to demonstrate a technology, or it could be something that flies in space. It could be a large telescope or radar dish, and it can be very complex at times. We generally only do one or two. Occasionally, we build several. 10 units for us would be a large number. So I'm going to share a little vision of the digital thread and digital transformation for you. So Carl, if you could just show the video, that would be fantastic. We playing that video? Okay, well, we seem to be having a problem with the video, so I'll just move on. But it basically says that we're building a connected environment for the evolution of engineering practice. So I'll just move on. So let's talk about the evolution of engineering practice. So much for digital. So if you think about engineering as a whole, and I'm a mechanical engineer, so back in 1765, the French invented projected view drawings, and nothing much changed in mechanical engineering until the 1960s. So if you're a mechanical engineer, we really had our day in the sun. What an exciting time. But in the 60s, digital technology started to be developed, electronics, computing power. And that was really the beginning of the information age and the beginning of the age of digital engineering versus pure mechanical engineering. So and technology has developed incredibly rapidly in that time. If you think of all of the changes in how we practice engineering, not just the things that we actually design. So we're moving towards digital representation of models. We're moving towards more connectivity. So if you think about kind of in the mid-90s, we all started to use 3D models in CAD, but then we added simulation to that. And all of a sudden, those drafting tools really became engineering tools. And that really changed the way you could look at mechanical design and the people that took part in that. And if you look at, a similar situation right now, is that model-based systems engineering is becoming prevalent in a lot of industries. And model-based systems engineering allows you to represent the system before you design the hardware. And now, as we're connecting MBSE to simulation and doing more and more things, we're starting to shift away from those domain-centric models like mechanical CAD models or electronic CAD models to having the system as the center of the design activity. And in 2018, the DoD actually released a strategy around everyone who takes part in development, saying we need to move in this direction to take advantage of these digital tools. And tomorrow morning, the keynote, Phil Zimmer is actually going to speak about this. So the shift then, the transformation, it's not just adopting tools, it's changing from the left, where you have a lot of people who are connected, but your data isn't, and you're passing paper back and forth. And that's very error prone. That's very difficult to manage really complex systems, to a transformed model where everyone is looking at a central model, and it's coordinated, it's connected. It allows you to be more agile and innovative because you can see a lot of connections that you couldn't otherwise using paper. So a word about transformation in general. And again, this is more than just adopting a tool. It's really shifting the way that we think about engineering. It's marrying intent to data so you can understand your design at a much more conceptual level. And just adopting those tools isn't enough. There was systems engineering before MBSE, and there will be systems engineering after MBSE. So MBSE is a way, or those digital models are a way to enhance the work of systems engineers, but certainly not replace it. But the real transformation is thinking about how people actually use the data coming out of those models. It's not about how the systems engineer uses it. It's how the rest of the organization does. And that's really where the transformation is. And that's a difficult thing in organizations where you have been permanently dealing with paper, because it's a whole different way of working together. So we looked at this and we came up with a strategy, and this has been about 10 years now that we've been working on this. But basically we said we need to represent everything we do in data and models. So where we might still use a CAD drawing, it would be derived from a model. And we needed to shift towards MBSE models and look at a lot of the other processes and look at the data that everyone in the organization needed from all of that paper. When we put all of that data on a platform, you can organize it however you want for purpose. So I call that reconstruction of that data, which is like a bunch of Legos into information, and it's for purpose information. If you can do that, you can get organizational value out of that, because you can start to find patterns in it. You can start to see things. You can start to have knowledge. You can start to have that interconnected workforce where people and data are connected to each other. So I'm going to give you an example of what that might look like, and then Tim will show you what it looks like on the platform. So if you're not familiar with MBSE, and it should actually say system model rather than the name of the type of tool, but a systems model represents things like your behavior, how something acts, what steps it will move through in a workflow, an architecture, the interconnect. So when you think about CAD models and software and electronics, they don't talk to each other, but you can define the behavior of all of them, and that can connect them together. Things like requirements and parameters, and you can simulate those. And we're actually using this now in our PLM implementation to start to see that our workflows are going to work before we ever actually code them up. So it's not just for hardware, we can apply it to PLM as well. So if you think about that, you can start to connect those domain models through defining the behaviors and requirements directly to your MBSE model. And that could be CAD, and there are various types of CAD tools, and CAD has its own set of simulation as well. So if you thought about MBSE and that systems model as being your virtual prototype, you could say, when I have the hardware designed, it's really a digital twin of my prototype, and I can simulate whatever aspects of it I think are important. As I move into actually fabricating this, and smart manufacturing could mean anything depending on what type of business you have, but it basically means that you use data in your fabrication activities. And there's automation and simulation in that as well. It could be CAM, it could be automated assembly planning, it could be a connected factory. So you can connect that directly from your models. So I can define my model, my CAD model completely, and pass it directly into my machining tool. Once I do that and I start to get feedback about the variance of that real thing compared to how I designed it, that would be a physical twin. So now I can start to see the changes from how I intended it to be to how it is. And then when I actually start to do physical simulation, otherwise known as test and validation, I can actually validate those requirements back in my systems model. And I can, if I do it in a smart way, it means that an army of people don't need to do it manually. The models all are connected so they can start to see that. And then I can also pass data back into my model and run those same simulations so that I can validate that the system is working the way I expected, or I can change my model, so I have a better model, and that would let me do sustainment in the future and run scenarios and improve either the hardware or the software. Now, the secret of all of this is that the models don't really connect to each other terribly well, so you need a platform, and that's what we use Innovator for. So we take all of these models and we're starting to connect them to the Innovator platform. And of course, you have a lot more features than just being a data bus. You have workflow, you have visualization, and you have a lot of tools that allow Innovator to be that central hub that everyone is looking at to get that information. And then once all of that information is there and that data is in the platform, we can think of the next level up, which is how do we get knowledge from that? Now, the great thing about having a platform in the middle of this is that we can tie all of our engineering tools to this, but we can tie our business tools to it as well. So there's the business of engineering that engineers don't like to think about all that much. So the MRP and the ERP and project management. And for us, technology transfer is really important, and being able to grab all of that data pretty much instantaneously off of the platform and package it up to send back to the government or an industry partner is really important. So the last thing I'm going to say before turning it over to Tim is that one thing to think about is resolution. So, or a common language. How much do you really want to tie together, or where do you get the value? So if you imagine you have a number of different types of models, and again, it could be CAD, they could be simulation, they could be requirements or an architecture, and you could tie the elements together, you could tie the models together, you could build those relationships within the platform. But if you really wanted to automate a lot of things like validation of requirements, you have to look one layer beyond that to a common parameter backbone. And what I mean by that is, as an example, let's say in your requirement model, you had you determined your requirement was in between 23 and 26 volts. And when you did a simulation, it showed 24 volts. You could automatically validate that that your simulation was showing that your system is going to work. And the same with test, and Tim will show you a little bit of that. So once you have that parameter backbone, there's a lot you can do with that. Generative design, you can start to think of things like, I have a requirement and it says the thickness of this component needs to be a certain value. and I can point out parametrically on my CAD model what value that is. But then when I actually measure the real part, if I can send that parameter back into my model and simulate it, I can show that my assembly is going to work before I ever start building it. And as we all know, building is expensive. So there's all sorts of opportunities there with really getting down to this common language. So my friend Tim is going to show you some of this live. So I'm going to hand that off to him. So if we could switch.
Thank you, Denise. I hope everybody sees my screen. We're going to have a little bit of PowerPoint, and we're going to jump into the demo. So my name is Tim Keir. I'm Director Pre-Sales North America at ARIS, and I will be demonstrating key aspects of the digital thread solution developed together by Lincoln Laboratory and ARIS. And the objective of this work was to expand Lincoln Laboratory's existing ARIS Innovator solution to include requirements, systems models, engineering data management, and simulation as part of a complete digital thread solution. Now, Lincoln Laboratory designs complex structures or complex systems using many different authoring tools. And ARIS Innovator doesn't replace these authoring tools, it connects them. So let's start in one of these tools, Cameo Systems Modeler. This is a block definition diagram of the system of interest. And at ARIS, we believe that we should leave information in the systems of origin as much as possible and only manage the business elements that are required for seamless interdisciplinary collaboration. So from Cameo Systems Modeler, we can save the data to the ARIS platform and then use a bidirectional connector to keep the data synchronized. No two organizations will use ARIS Innovator and Cameo Systems Modeler in exactly the same way, and so we need the flexibility to deal with different data models in ARIS Innovator and different data models in Cameo Systems Modeler. And the ARIS connector is therefore configurable, allowing the appropriate maps between the two tools. So in ARIS Innovator, we see the same system after synchronization. Let's use a digital thread view to explore the system structure. We see the same system elements that we see in Cameo, but here we've expanded the digital thread view to see the physical abstraction layer, the P of RFLP. And in this instance, the P layer includes parts and engineering data containers. We'll talk about parts in a moment, but let's focus on engineering data containers. Engineering data containers, or EDCs, contain tool-neutral engineering data. They are the single source of truth for data that will be used by various downstream activities, including simulation. And EDCs can represent design data, masses, simplified geometry, stiffnesses, and they can also represent environment data. So here is an EDC, an engineering data container for a convection boundary condition. And the user can create different versions of the EDC with different values for the convection coefficient and the bulk ambient temperature. And then the user can use these different versions of the EDCs in different simulations. And let's navigate to the simulation study that uses this data. A study is the top-level simulation-related item, and it asks the big questions. Will this system meet its requirements? Or perhaps more usefully, how can we ensure that the system will meet its requirements? And a study contains simulation tasks which represent a single simulation or a simulation step. So let's look in more details. A simulation task allows simulation engineers to create, launch, and manage simulations from inside the ARIS platform. And I see that this simulation is a thermal simulation performed using SolidWorks simulation, and it was performed automatically using ARIS Comet, ARIS's simulation automation engine. We can see the inputs that were used. So here's the design representation. this is a part, and we can check the exact revision used in the simulation, and we can visualize the geometry. I'll just wait for this to be prepared. This is the geometry of the system that we're looking at today. We can also look at the environment representations, the engineering data containers, the EDCs that we looked at earlier. Now, I mentioned that this simulation was performed automatically. So after specifying the inputs, the user launched the simulation, and Aris Innovator took care of running the simulation. When the simulation was completed, Aris Innovator imported the results. We see the maximum temperature was 1.99 Celsius, and the platform automatically assessed whether the results met the associated requirement or not. The requirement had the target range greater than -3 Celsius and less than 3 Celsius, and because 1.99 is between -3 and 3, we see target met, good. But it's rare that only one simulation task is required, and design space exploration is typically used to improve the design to make it lighter, stiffer, stronger, easier to manufacture, and so on. So using the simulation's digital thread view, users can track the different versions of simulations performed, and they can also compare results in a single table like this. Different simulations, descriptions, and results. Sometimes we meet target, sometimes we don't. So let's finish this quick demo by talking about requirements and the digital thread. This is the requirement that we just used to assess our design's performance as modeled by simulation. And here are the expressions used to define pass and fail. And let's look at the digital thread view of this requirement. I can see that requirement 178 was verified by test case 46 using study 3, which contained simulation task 94, whose result is green, indicating that the requirement was satisfied. That closes the loop, verification and validation. So to summarize, back to PowerPoint, I've shown how Lincoln Laboratory uses the Aris platform to create and manage a strong digital thread, connecting requirements, systems architecture information, engineering data, simulation, and then closed loop verification and validation. But the digital thread is not just about connecting data, it's about connecting people and teams. Simulation engineers have access to all the product information that they need, and in turn, product engineers have access to all the simulation information that they need. And systems modeling and simulation, two important disciplines that have tended to exist in silos, can now be a much better integrated part of the development process. So this is the implementation of what Denise was describing earlier. Thank you for your attention, and back to you, Denise.
All right. So thank you, Tim. That was a great demo. So just in conclusion, we're happy to take questions if you want to enter them in the Q&A in your viewer. So, you know, the world is getting more complex. The technology we develop is getting more complex, and these are really techniques for helping humans manage that complexity and interact in teams. So, you know, digital transformation is focused on consumption. How do others consume the work that you do? How do you bring value to your organization by allowing that consumption? You know, that visualization that you saw is critical to that. And something we didn't show you, but John Sperling mentioned this morning, knowing what you chose not to do is sometimes just as important as knowing what you did. So we also have variant management in there, and we can look at different options. So, and that allows us to also in the future start to do more of that knowledge capture of why we didn't do certain things, what worked and what didn't work. So in conclusion, digital engineering is really about having a pervasive traceability of the digital thread. It's connecting that intent with data, and the transformation that digital engineering promises is more effective use of technology and of engineers. Build it all with data and connect the people and connect the data together. So thank you for listening. We have about 5 minutes. Both of us are happy to take questions.
So Denise, I see a couple of questions in the Q&A box. Would you like to answer them? Would you like me to?
Sure. Let me answer Michael's first. So right now, we chose. So we're in.
You might want to read the question because you might want to read the question because other people won't see it.
Which tools are performing the simulations? Sorry, I forgot you all can't see this. Right now, we're doing we did a POC and we're just about to start full implementation. So we actually chose SolidWorks simulation as the first step. We have a very broad set of tools that are on the roadmap, but we chose one that a lot of engineers are using that we thought would bring the most value to the organization immediately.
Yeah, I'd add that Aris Comet, the automation engine that we used, has connectors to many additional simulation tools, some of which are used by Lincoln Laboratories, some are not. We support the use of many different simulation tools for simulation from Aris Innovator.
Right, and okay, so we have another question from Stephen. Hi, Stephen from Sandia. Are engineering data containers a feature of the Innovator platform or something custom developed as part of the LL solution? Actually, Tim, I'll let you answer that one.
So engineering data containers were first developed for a proof of concept for Toyota Motor Europe. The initial EDC implementation was using what we used to manage design data. We've now expanded their use at Lincoln Laboratory for environment data that I showed here. So they're not a standard part of Innovator out of the box. Of course, one of the strengths of Aris Innovator is its configurability. And so having configured it once or twice, it's very easy to reuse those configurations elsewhere. And of course, you don't have to worry about configuration taking you down a dead end, because Aris Innovator will always upgrade you to the next version without having to worry about the cost of reconfiguring things. So engineering data containers are being used at various different companies or various different customers around the world. Toyota Motor Europe and Lincoln Laboratory are the two best examples.
Okay, so we have another question. I'll answer half of this, and I'll let Tim answer the other half. So from Peter, how much effort is it to keep the connectors to the Aris platform current? So I can answer you. So we've connected Mentor Graphics, SolidWorks, SAP, Office. Those are our main platforms, and then again we're doing this POC. So I'll answer you on the CAD tools. We have waited occasionally for the platform connectors to catch up. So we just finished a major upgrade not too long ago, and that was actually drove us upgrading our CAD. It wasn't by much, it wasn't by years, but we did have to wait, and I think Aris is trying to address that, as you heard this morning. But Tim, I'll let you answer that on the simulation side.
Because the Aris platform is open, that removes a big barrier to keeping the connectors up to date. Aris develops connectors, our partners develop connectors, and the open nature of the Aris platform makes it easier for customers to develop upgrades than if we had a closed or proprietary data model. Some connectors are easier to upgrade, some are not as easy. But I haven't noticed a big lag affecting our subscribers' ability to use those connectors.
All right, I think that's all we have for questions, and we're just about out of time. So unless there's anything else, thank you everyone for attending.
Yeah, thank you for your attention.